Hello dear student, I am Monroe Islam. Today in this video we are going to discuss an important question from CSIRNET June 2021. This is basically a question from Part C and it is question of topology. Okay, and question ID is 525 and it's a 4.7 mark. The question is X is a topology space and EB is subset of X. Okay, it is saying X is a topology space and EB is subset of X. Then there are four options and among this which are true. Okay, first option is true. Okay, it's always true. We all know this result. If a set is connected, then its closure is always connected. Okay, but I am giving a small proof for this. Okay, for option 1, I am considering X to be usual topology. Okay, so the proof becomes simple. And suppose E be a subset of X. So E may be empty set or non-empty set. Okay, if E is empty set, we all know empty set is connected because it can be written by interval open one. It is empty set, interval is connected, so it is form of interval, so it is connected. So E is connected. Okay, now then E bar, if E is empty set, then E bar equal to phi bar and closure of phi is R, and R is an interval. Okay, you can write it like this, minus infinity is connected. Every interval is connected, non-usual topology connected. So if E is equal to phi empty set, then E bar is connected. Okay, now if E not equal to phi, E may be not equal to phi, non-empty set. Okay, then you have to also conclude that E bar is also connected. If not, E notify and E is connected. Okay, given because in option 1 it says if E is connected then E bar connected, so E is connected is given. Okay, now if we assume that E bar is not connected, suppose I am assuming that E bar is not connected. Okay, I am assuming that E bar is not connected, then we can write E bar like this: union of two set. Okay, A union B, where A is non-empty, B is non-empty. Okay, and both are open or closed. Okay, I am taking open. Both are open in X for my convenience, and with their disjoint, A intersection B is empty set. Okay, so E bar can be written as A and B, where A non-empty, B non-empty, and A, B are open in X, and the A, B are disjoint. Okay, now in this portion is expression, if you take union both sides by E, then what you can see? If I take union by E on both sides of this, I am taking union on both sides of this by E. If I take union on both sides by E, then it becomes E union E bar. Okay, then it becomes A union B union E. Okay. Okay. Now we all know that E bar is the closure of a set, is the smallest closed set containing E. Okay. Closure of a set is the smallest set, closed set containing E. So this set containing this set, containing this set. So it will be intersection, right? I am taking intersection. Taking right like this. E intersection A union. Okay, I am taking intersection, not union. So since it is small set, so E intersection will be E. Okay, now, by this property you get E intersection A union E intersection B. Okay, by commutative property you can write A intersection E union B intersection E. Okay, so E can be written as two set. Okay, first of all name this set is C and name this set is D. So E can be written as C union D, union two set. If we now what can we we can draw conclusion about C and D. What CRD? CRD are what? By using the concept of the data of A and B. Okay, I am assuming this C and this D. And then first thing, C equal to A intersection E. This set is open because this set is open in X, in whole space, right? Open in X. This set is open in X, and yeah, if I take open intersect with E, then by subset topology this become open in E. Okay, similarly D equal to A intersection B intersection E, right? Since B is open in X, B intersection E. Okay, right? Now B is open in X. If I take intersection with E by subset topology, this become open in E. So both C and D are open in E. Okay. Also, if you observe C intersection D, then you get disjoint. Okay. Write C and D, C intersection D. What is C? C is A intersection E. Okay. Intersection B intersection E. So you can write like this: A intersection B, and E intersection E gives E, but E intersection E is phi, and E is non-empty set with intersection with phi gives phi. So C and D are disjoint set. So C and D are both open set and disjoint. Okay. Also, since A is non-empty, E is non-empty, B is non-empty, then this gives intersection A intersection E. This is C also non-empty. Okay, and D means B intersection E is also non-empty. So I have written C as a E is a union of two set. It is C and D. E is a union of two set. Write it like this. E is a union, I have written C as a union of two set, C and D. Okay, where C is an open set in E, D is also an open set E. Also, in these two are non-empty, and their intersection is phi. Okay, empty set. So what can we get conclusion about E? Then we can say from this E is disconnected. Okay. So till now what I have done, I have done this. E is written as C non D. Okay, but C is non-empty, D is non-empty, and C and D are both open in E, and C intersection D is empty set. So the empty set, and C intersection D is empty set. So E can be written as union of two sets where both are non-empty and both are disjoint open set. So from this we can say that E is disconnected, E is not connected. Okay, but it is a contradiction. It is given that E is connected. Okay, it is given that it is a contradiction. It is given that E is connected. So E bar is not connected. So if we assumed previously that E bar is not connected. Okay, so this is contradiction. So E bar must be connected. So E bar must be connected. So E bar must be connected. So what we will set E? Either E is phi empty set, then it's connected, is closure R connected, and E is non-empty, then it is also connected. So in any case, E bar is closure of a set E is always connected. For any set subset E subset X. Okay, so option 1 is correct. For any set E subset X, then closure is always connected. Now go to option 2. It said E is connected, then E delta is boundary is connected. Okay, it is not true. Okay, just one example is sufficient for this. Option 2, X take X is equal to R tau. Okay, and take E is the set this close one. Okay, if you observe this, in the set there are 0, 1 and input member. Okay, then E is connected. Okay, we all know E is connected. Why? Because it is interval. We all know in R is topology, interval only interval connected. Interval and single set are connected. Okay, only. Then it's connected. Okay, because it is interval close one. Then if you find boundary is 2 point 0 and 1. Okay, so it is not an interval, not a single set. In topology, it is not an interval. Okay, because in between point are not interval means in between point also in the set, but in between point are not in the set. So it is not an interval, not in single set, because it is a two member. So it is not connected. Yeah, so it is not connected. So it is not connected. So E is connected. If you choose E close 01, if you also choose another example close 02, close 03, close 04, you can change example accordingly. Okay, I have just taken for my convenience close 01. So E is for this example, if I choose E equal close 01, then E is connected, but E bar is just set containing 0 and 1 is not connected. Okay, so option 2 is incorrect. Now go to option 3. You said E is path connected, then E bar is path connected. Okay, if E is path connected, then E bar is path connected. For this I am giving a nice example. Okay, I am giving a very beautiful example, and we all familiar with this example. It's called topology sine graph. Topology sine graph. Take X equal to R2 with E topology tau. Okay, and takes the set E the curve X sine 1 X sine 1 X. X obviously greater 0. Okay, because if X is 0, then it is not defined sine 1 X. Okay, if you try to draw this curve. Okay, first of all, X greater 0. Okay, X may be X greater 0. X and Y axis. Okay, now we all know mod sine y. This expression mod we all know mod sine y is always less equal to 1. Okay, so this is xy, so this is y equal to fx. Okay, you can write this fx. So here in this case y equal to fx equal to sine y. Okay, we all know sine y mod is less equal to 1. Mod of sine y is always less equal to 1. Okay, so the values of y lies between 1 and -1. This is 1, -1, this is -1, this one. The values of y lies between 1. Now if you observe this 0, if you put sine inverse is 0, you put sine inverse is 0. Okay, then what gives? It gives 1 upon x equal to n pi. Okay, in channel 1 2 3 so on, and x equal to 1 upon n pi, because n, if n may be integer, but in this case since x greater 0, n can never be negative integer, because if n is a negative integer then x is a negative integer. If n is a negative integer, suppose n is -1, then it gives x equal to -1 upon pi. Minus x, if n is -1, then x equal to -1 upon pi. But I have taken s greater 0. Okay, so this is not possible. So only I have taken n greater than 1. Okay, so x equal to 1 upon n pi, where n is greater than 1. So it 0 are on the set, 0 are 1 upon pi in the set. If you put n equal 2, it is 1 upon 2 pi. If you put n equal 3, so it gives 1 upon 3 pi, like this. So this is the 0 of the set. So function will be like this, and it is oscillate because it never goes to 0. Sine inverse is always never 0. Sine it doesn't touch the line always. Okay, it oscillates between this. Okay, so this is the curve E, and we all know this curve, a curve is always path connected. Okay, because if you take a point here and take a point here, then you can always go through this path, and this is a continuous path, and this is a path mean a continuous function. Okay, you can say continuous function. So if you take a point here on the curve and take a point here on the curve, then you can go through like this. Okay, around this curve. So if you choose any other point on the curve, then always to the curve, then you can connect that point. Okay, so this curve is path connected. This curve is always path connected. I can say this curve is path connected. Okay, but it closure is not path connected, because if you take it closure for set E, what is the closure? For the set E, the closure will be E non E dash, means it contains E and a limit point. Okay, but for this curve, the limit point will be every point on the curve a limit point. Okay, because if you take a point here and take it near open ball, okay, and exclude this point, then it contains also other point, because in the point in the boundary, this point and this one also in the intersection. Okay, so every point on the curve a limit point. And also if you observe 0 0 is limit point, because if you take a neighborhood about 0, and this curve also in here. So if you take a neighborhood in 0, so suppose the neighborhood B0 0 and epsilon radius. Okay, epsilon radius, then and exclude the point 0, then if you intersect with E, then it gives many point. Okay, many point in intersection, because the curve is oscillate between this. Okay, so it gives many point with intersection with E. So B dash 0 with epsilon radius open wall. Okay, B0 intersection E is 0 is the center of epsilon radius open wall, and exclude the point 0, then it gives intersection always with E non-empty. So it means 0 0 limit point. 0 0 is a limit point. Also, if you observe the point on the line, this line segment between 1 and -1. Okay, if you choose a point here on the line on -1, arbitrary point, suppose it is name is 0 0 half. Okay, 0 half. Then if you take a neighborhood this, suppose the neighborhood is radius delta, so I am choosing the neighborhood. So suppose the point is b0 half and the neighborhood epsilon radius, then exclude the point 0 half. Okay, then it also give an intersection with E. It also give an intersection with E. Okay, always give intersection, because this between the curve is oscillate. Okay, curve is oscillated, so also it counts. So 0 half is also a limit point. Similarly 0 1/3, 0 1 for every point on the line, this -1 is also a limit point. Or I can say this point, because every point on the y axis will be from 0 y, and y ranges from -y to 1 is also a limit point. This set is also in the contained in the limit point set. Okay, so 0 0 can be limit point, and every point on the curve on the limit point, and every point on the line segment, this ranges from -1 is also a limit point. So what are the limit point set for this curve? So I am writing the set of limit point. So what are the limit point set of this curve? Limit point, first of all, E is the set of limit point. 0 is also on the limit point, and also the form 0, -y such that -y less than y less 1 is also a limit point, set of limit point. Okay, but see 0 0 is included in the set, because if you take y equal to 0, because minus 1 in between minus 1 there is 0, so 0 0 is in the set, so you have not take 0 0 here, because 0 0 is also included in the set. So just take union E and this set. Okay, is the set of limit point. So set of limit point will be curve, every point of the curve with union with this set 0, y such that minus y less than 1. Okay, so if you find the limit point set, then you can easily find the closure of E equal to E union E bar. But see, in the E is also in the present index E bar. Okay, so you have to write E. What is the E dash limit point? E bar equal to E union E dash. E dash is E union this set. So you have to take E union 0, y such that minus y less than 1, right? But E union E gives E, so it gives 0 union y such that minus 1 y less than 1. Okay, this is the closure of the set. This set is the closure of the set. Closure of the set E. Closure of the set E. See, this set is not path connected. This set is not E is path connected. It is a curve. See, E is a curve since it is path connected. But see, E is a curve, then every curve is path connected. Is path connected. But its closure E bar is not path connected. It is not path connected. Okay, why? You can see the graph. If you see the graph, you can easily understand. It's not path connected. This is the curve. Okay, minus in between minus 1 it lies, and 1 upon pi 2 pi is 0. It goes through like this manner. Okay, if you in see in here is 0 0 in E bar, right? 0 0 in E bar, 0 0 in E bar. So take 0 0 and take another point on the curve. You take in this point. If you join, can you join this point by a continuous path? Never, because if you join this by continuous path, then this point not in the set. Okay, because E bar is the set of the point on the curve in 0 0 and with the line segment in between this line segment point. Okay, not the point on this axis. This point, this line segment, the point is the point that are not in E bar. Okay, so if you join these 2 points, then the line segment join these 2 points goes outside the set E bar. Okay, so E bar is not path connected, because the line segment, if you join the point, then join to a point, then the line segment should be in the set, this set. Okay, but in this case the line segment is lying outside the set. Also, you cannot never join this point. If suppose if you choose a point here, suppose it's 1, 2, and this point, can you join this point by a path, any continuous path, such that this path always lies in the E bar. Okay, never. Then this path going outside E bar. If you join, you can join this 2 path. Okay, join, but the path going outside to E bar. So E bar is not path connected. Okay, so E bar is not path connected. So for the example, E bar is not path connected. Okay, so option 1, option 3 is incorrect. Is path connected, E bar is not path connected. Okay, now the last option. It said E is compact, then E bar is compact. It's very trivial. Take just very simple example. Take let x equal to R with equal topology. Okay, type, and take E equal to empty set. It's not saying here E is non-empty. No, I take empty set. Not saying E is empty or non-empty. So I take empty set. E equal to 5. Empty set can be, empty set is a finite set. Okay, we all know finite set. We all know finite set is compact. Every finite set is compact. Since every finite set is compact, then we can say from this, then E is compact. E is compact on usual topology. Okay, but if you find E bar, what is E bar? E bar will be 5 bar, and closure of 5 will be R. Okay, we all know R is not compact, because R is not bounded by Hannibal theorem. Yeah, Hannibal theorem, subset of R is any subset of R is compact if only it is close bounded. Also R, since R is not bounded, it is not compact. Also you can go through the cover. If you look on the cover, it is open cover, -1, open interval in greater than 1. This is open cover. Okay, this is an open cover of R. This open cover has no finite subcover. You can never get finite subcover, such that cover also cover R. This is an open cover. This is an open cover of R. Okay, because R can be written, R can be contained in the set -1 in greater than 1. Okay, so this set become open cover. In -1 in greater than open cover, this open cover has no finite subcover. For this open cover, you never get a finite subcover. So R is not compact. Okay, also R is not bounded. You can also conclude from Hannibal theorem. So R in here, then you have R is not compact. Okay, so if R is E bar is not compact, but E is compact. Okay, so for says E is compact, E bar is compact. You know, right? Just take E equal to empty set, take E equal to E is empty set, E is 5, then E bar become R is not compact. Okay, so this is incorrect option. So in this question, correct option are only option 1. Okay, so in this question, correct option are option 1 only. So if you any doubt, you can always ask in the comment section. Okay, and more video solution will come in the upcoming videos. And if you any doubt in the particular question, you can comment me, you can tell me about this question. Okay, I will take the question in the next video. Okay, so thank you.